Hello everyone. Today we will introduce a new element, the CMOS. It's derived from the MOSFET. Here C means complementary. What's the complementary things and its advantage? Firstly, let's analyze the power loss of the logic gates formed by the MOSFET. Take the inverter as an example. When UGS is 1, the MOSFET is turned on and acts as a resistor seen from the drain and the source terminals. This is the circuit model. There is a current path, and the power loss of the logic gate contains the power loss of RL and R-on. We assume the typical value of RS, RL, and R-on is listed here, that is 5 volts, 100 k ohms, and 1 k ohms respectively. So the power loss of the logic gate is calculated to be 0.25 milliwatts. Don't underestimate this value. For a single logic gate, it's a tiny power loss. But there are hundreds of millions of the transistors in a CPU. We assume there are about 40 million transistors in a CPU, and all of them are made of N-channel enhanced MOSFETs, and all of them are formed into the inverters. Then the power loss of a CPU is about 10 kilowatts. It's really a huge value. You all have the experience of using a computer, and it's obviously unacceptable, and the actual situation cannot be like this. So how to decrease the power loss of the logic gate? From the equivalent circuit, you can find one of the improvements is to decrease the voltage of the power supply. In fact, this is also the approach taken in electronic industry. The CPU's power supply voltage has been decreased from original 5 volts to 3 volts later and to less than 2 volts today. The aim is to decrease the CPU power loss. However, there's a limit to this decrease. The low power supply voltage has an impact on the reliability of the CPU, so it's not a fundamental approach. Can we suppose if there's no current path when the MOSFET is turned on, then the power loss is zero? In other words, can we improve the logic gates structure to ensure there's no current path when the MOSFET is turned on? Thus, the power loss is completely eliminated. This is the original intention of the CMOS. Our previous analysis is based on N-channel enhanced MOSFET. This is its circuit symbol. When UGS is greater than UDS plus UT, that is, UDS is less than UGS minus UT, the MOSFET is turned on. And acts as a resistor. Corresponding to N-channel enhanced MOSFET, there's a P-channel enhanced MOSFET. This is its circuit symbol. Pay attention to the difference between the circuit symbols of N MOSFET and P MOSFET, the direction of this arrow. The operation mechanism of the N-channel MOSFET and P-channel MOSFET are basically similar. The difference is when P-channel MOSFET is connected to the external power source, the S terminal is not connected to the negative electrode of the power source, but to the positive electrode of the power source. So its turn-on condition is that USG is greater than USD plus UT. With this condition, the MOSFET is turned on and acts as a resistor between its drain and source terminals. For distinguishment, the resistance is represented as R on P, and this is represented as R on N. Connect the drain terminals of N-channel MOSFET and P-channel MOSFET and N-channel MOSFET together. Connect their gate terminals and apply the same control signal. A new element is called CMOS is formed. Complementary is derived from the complementary structure of the P-channel MOSFET and N-channel MOSFET. Let's see the function of the CMOS connected to the logic signals. The source of the PMOS is connected to the high level, that is logic 1, and the source of the NMOS is connected to the low level, that is logic 0. Now put a logic signal in. If the input signal is logic 1, for the PMOS, USG equals 0, since its source terminal now is connected to logic 1, 2, while for the NMOS, the UGS equals logic 1. Therefore, for the PMOS above, it's turned off because USG is 0, while for the NMOS below, it's turned on because UGS is 1. The conduction in resistance is R on M. Since there's no current path, U out equals logic 0. The output is 0 when the input is 1. Next, consider the case that the input is 0 for the PMOS above. USG equals logic 1 since its source terminal is connected to logic 1 now. For the NMOS below, UGS equals logic 1 since its source terminal is connected to the ground. Therefore, the PMOS is turned on since USG is 1 and its conduction resistance is R on P. The NMOS below is turned off. We can see there's no current path. So U out is connected to the high level, that is U out equals 1. Let's look at the two logic relations. When the input is 1, the output is 0. When the input is 0, the output is 1. This is right for the logic of the inverter, and in fact, this is the inverter formed by CMOS. Compared with the previous inverter formed only by the NMOS, there is no current path inside the logic gate, no matter what input signal is. So the inverter formed by CMOS has no power loss in steady state. It is really exciting. Now please think about such a question. The complementary structure of the CMOS we discussed just now is PMOS above and NMOS below. Can their position be exchanged? In other words, can we realize the logic of the inverter correctly after exchanging their positions?